Okay, so today, which is the 10th lecture, we are going to finally talk about the key concept behind general relativity. And in the very first lecture, I talked about the importance of having universal laws that don't change when we go from one frame to another. At that time, I might have mentioned Galileo's imaginary ship experiment of being closed in the cabin of a ship and not seeing outside. And then you wouldn't know if you are at rest, if the ship is at rest or it's moving in the water, as long as the motion was smooth. And that thought experiment inspired Einstein to ask something similar. Okay, first of all, that thought experiment gave Galilean relativity, and that was a reasonably correct thing to do for a long time, till people realized that, well, it contradicts the fact that the speed of light is the same in all frames. So that forced Einstein to go in the direction of special relativity. So different transformation laws, but and they have to preserve the speed of light. But other than that, they do that job of making sure the laws of physics are the same in all inertial frames, whether stationary or moving with constant speed. So Einstein tried a different thought experiment, and he said, well, shouldn't laws of physics really be the same under all changes of frame, not just inertial changes of frame? And immediately we run into a huge potential contradiction, because if I make an arbitrary change of frame, then there's no uniform velocity. There could be anything, acceleration, or the velocity can change at any rate it likes. So the frame in general, which is not inertial, will be accelerated. So inertial frames is fine, we understand them. But now supposing we want to go to accelerated frame. When I say accelerated, I don't mean with a constant acceleration. I just mean any frame that's not inertial. Okay. Now, because of the knowledge of special relativity, which says that the transformation to such a frame is x mu goes to x prime mu equals lambda mu nu x nu. This encompasses all the Lorentz transformations as long as lambda satisfies this equation. This takes the place of all the Lorentz transformation formulae in your textbooks. Okay, and it also includes rotations, which will happen if lambda has no components with any of these being 0. If it's just lambda ij, and then when it's 0, lambda 0, 0 is 1, then time doesn't transform. In that case, this condition will simply make lambda orthogonal, and we'll get rotations. The rotational invariance is also good. It's part of change of inertial frame. So everything is good here. So the question to ask here is, for a general change of frame, what should be x prime mu in terms of x? And the answer to that is that it should be anything. Not this constant matrix multiplying the original thing, that's a linear transformation. In this case, it's just anything. Well, not completely anything. In this case, lambda was invertible, so we could go back from x to x prime. In this case also, the transformation should be invertible. Okay. That's important. We don't have a simple criterion to write what it means to be invertible, because it's a function. We know the meaning of an invertible function. If it takes you from this side to that side, it should be possible to have a function f inverse which takes you from that side back to this side. That's all it means. Just has to be said in words. Okay, so this was a question. Now, we don't always ask unmotivated questions in physics. They often lead nowhere. You could just ask the question. There are similar questions even today you can ask, and without a motivation, you won't necessarily either find an answer, or even if you find an answer, it may not end up being useful. So there has to be some physical motivation, and there's quite a list of them. So let's list the motivations and then see why this is a good question, and then we can easily see what the answer is. In physics, it's often more important to have a good question than to find the answer, because without a good question, you're not going to even look for the answer. With a good question, you may find the answer. So motivations are as follows. These are motivations to ask this question, that can the laws of physics be invariant? Okay, so first of all, there are several special cases that already make sense of this transformation law. And actually we have spent all our time since beginning of this course on those special cases. What are they? X prime mu equals lambda mu nu x nu is a special case of that. Arbitrary function, I specialize it to a linear function where lambda satisfies that condition, then it's a special case, and this gives me special relativity and it's correct. And it's confirmed experimentally, so this is a good thing. Okay, B, you might notice that this also includes rotations as an even more special case where xi goes to some omega ij xj and omega is transpose omega is 1. It's a special case of that. We've seen that. So this is a special case of the general coordinate transformation. This is even more special case. Rotational invariance is an excellent invariance of the laws of physics. All the laws of physics that you have learned from high school or even before are rotationally invariant. That's why we use vectors in those laws, like del dot E or del dot B. All those constructions are there to make the laws rotationally invariant. Okay. There's another special case which was not taught to you for sure in school, which is the special case where xi goes to xi prime, which is an arbitrary function of x, while t doesn't change. This is also a special case of this, because here all the 4 x's transform in an arbitrary way. Here 3 of them transform in an arbitrary way and 1 doesn't transform. What do you know about this one?
This is like rotations.
No, it's not just like rotations. X prime I is an arbitrary function of x.
Just accelerating flow.
It's not an accelerating frame. I'm only changing the spatial coordinates and I'm doing nothing to the time. I'm not changing my frame. See, there's one mistake that people make. Change of coordinates and change of frame of reference are the same only if I change space-time coordinates. If I only change space coordinates, I'm not going onto a ship or any moving object. Okay? Okay. Sorry, good. I should have been more careful. These x prime are only a function of x, not of t. Okay, and I don't change t. If they are only a function of x, not of t, then I'm not moving to a frame which is in a time-dependent way changing from the original one. It's not a different frame, but it's a different set of coordinates.
It's
So-
like the regions of overlap in our Riemann.
Exactly, this is exactly Riemannian geometry that we've been discussing for the last 2 lectures. What is the requirement in Riemannian geometry? That there's a geometric structure, namely a metric, which is such that when it transforms as a tensor, the laws that you can write down or the geometry that you describe is invariant under this change, as long as this change is invariant, is invertible, which of course it inherits that property from this one. And these are all invertible. So this is the case of Riemannian geometry. Now, one doesn't often talk of physics being tested in the presence of Riemannian geometry, but it's sort of assumed that if there is a geometry, physics will obey the laws of that geometry. And certainly doing physics on a sphere is something we have done for centuries. Okay? And even using spherical polar coordinates, even where there's no sphere, that also involves going from x to x prime. And we know that the laws can be written in a way, see, if the laws are written in the Cartesian coordinates, then they are not invariant under this change. But if we replace those laws by the laws with a metric, and we transform the metric as a tensor, then this is an invariance of the laws of physics, even undergoing from Cartesian coordinates to spherical polar coordinates. So those are simple examples where this is certainly known and tested and important, useful, everything. Okay. So with all of these things, there's still one more I haven't written. Can anyone think of yet another known symmetry of nature which is incorporated in general coordinate transformations?
Translations in general.
Thank you. Very good. Translations. That's all, where alpha is constant. These are all special cases. So it's very natural to go to the general case and ask questions about it. Good.
Can you have the spatial coordinates remain the same as the time coordinates?
Translation, yes. Okay. And also in Lorentz transformations, the reason you can't have it is this requirement that lambda transpose eta lambda should be eta. You will find that just transforming the time cannot satisfy that. But shifting the time you can do. And we do it all the time. When we say our time starts from 0, we are shifting the time origin. So in the time case, this would be a 4 vector which would have only a time component, then it would only shift the time. Good. Okay. So here's the proposal. And we'll see the thought experiments later, but first let's see the proposal. I'm not going to use his words. I'm going to write down the way it would be said in modern language. Is a pseudo Riemannian. I'll explain that in a minute. Manifold with metric. And here x means x and t. For once I'll write it explicitly, everything. So the metric is on space-time, not on space. And this word means it doesn't exactly follow the laws of Riemannian geometry. The reason it doesn't is in Riemannian geometry the metric has to be positive. Here it need not be positive, because in fact the space-time interval, which is invariant, ds squared, is g mu nu of x dx nu. And if we want to understand intuitively what this is, we have a simple case which we have already worked with, which is where g is just eta mu nu, the Minkowski metric, and it is -1, 1, 1, 1, and then everywhere 0. Okay, and because the Minkowski metric has a minus sign, this invariant interval need not be positive, and that's why we saw in special relativity that we can have intervals which are time-like, space-like, or null. Okay, well, the same has to be true here, because g mu nu equals eta mu nu has to be a possible special case of this metric on pseudo-Riemannian manifold. And in that case, we certainly know that it's not a positive matrix. It has 1 negative eigenvalue and 3 positive eigenvalues. So actually, we require in general that g mu nu has a signature minus plus plus plus. Signature is nothing but the sign of the eigenvalues. So if it has one negative and three positive eigenvalues, we write it like this. And Minkowski metric does have that property. In fact, it's already diagonal and with that property. But now we require the metric of this pseudo-Riemannian spacetime to always have that property. Yes?
Can it be plus minus minus?
You can, that is a convention. Even Minkowski space, we could have chosen this to be plus minus minus minus, and some textbooks do that. There are many historical choices. Sometimes also people took all of these to be plus, but then the x0 coordinate was called I times t, where I is the square root of -1. Sometimes it was called x4 instead of x0. But the consensus today is that in gravitation, all of gravitation discussions today, whether it is in astrophysics or in formal gravity or in study of gravity waves or anything, this is the convention that's always used. So it's a convention, obviously. But whatever convention you use, this is not going to be necessarily positive. It still has the chance to be positive, negative, or zero. So in this way, it differs from a Riemannian metric. And that's the meaning of the pseudo. Only that. Sometimes it's also called Lorentzian manifold. That has the same meaning. Yes?
How can we say that general metric will have that signature?
Good. Because good. So if it doesn't have that signature, then we will, okay, so what signature could it have? All for plus? In that case, we will never be able to interpret one of those coordinates as time. Remember one thing, this has got to be a manifold. Let's remember that part. In a manifold, I take patches of my space and I map them to patches of Euclidean space. Now, what is the metric that I should put on that Euclidean space? I can't keep changing it on different patches. Otherwise, I'll never have differentiable functions. Okay? So, the metric on that Euclidean space is the Minkowski metric always. Now. Okay? So, therefore, the patch on the manifold also has to have that metric locally. We are going to see more precisely what locally means. But in any particular region, or look at it from common sense point of view. Right now, the Earth is accelerating, it's going around the Sun. Do we have any doubt that time and space are different things? And that if I want to go from one event to the other, then longer space means I'll be going slower, and on the contrary, longer space distance and shorter time means I'm going faster, and short space distance and longer time means I'm going slower. We don't have any doubt of that. We don't say that special relativity is wrong. It's just approximate. This is supposed to be more general than special relativity, but it can't fail in those situations where the metric is very close to the trivial metric, which is that one. Yes?
Also, the triangle inequality will not be obeyed.
Yeah, triangle equality therefore is not obeyed. Very good. In fact, what actually happens is hugely complicated, and so Lorentzian geometry or pseudo-Riemannian geometry is a whole subject of study which has new features relative to Riemannian geometry. But instead of focusing on those new features, let's focus on why he would think such a thing, why he would make such a proposal. And there's again a thought experiment behind it. And later then we'll develop the theory of space-time having this invariant. So this is again called the invariant interval. See, the good thing is now you know all these concepts in the case when G mu nu is eta mu nu. You know everything about it because we spent something like 5 lectures developing exactly that. Okay? So when G mu nu is eta mu nu, the story is known. The problem is, what if it's not eta mu nu? Or what if either by a change of coordinates I made it not eta mu nu, or what if it's a manifold in which eta mu nu isn't a possibility to choose? Just as with Riemannian geometry, there are manifolds like spheres where delta ij isn't a possible metric everywhere. So we have to come to grips with all that, and we'll do it slowly. So here's the thought experiment. Yes. Not holding? Okay, hold on, we'll come to it. These are all mathematical properties. We can easily, the statement I've made, you can easily check on your own. You can already see it with the Minkowski. See, today I am doing something going beyond special relativity. If the question you're asking is already a question in special relativity, triangle inequality does not hold. And let's answer your question because it's 1 minute. Just a diagram will do it. Space-time diagram. Okay. So supposing my triangle is this. These two sides are exactly at 45 and this is vertical. Okay? This is my triangle. Now triangle inequality says that sum of length of any two sides is greater than length of the third side. But now in space-time, length is not length. Length is ds integrated over that segment. Okay. What is this is exactly at 45. So what is ds between here and here? Integrated 0 because it is null. What is ds from here to here? 0 because it's null. What is ds from here to here?
Negative.
Integral of ds is simply the total time t. Okay? ds itself is imaginary, so we go to proper time. Huh?
This would be minus with a minus sign.
What?
In this case. So
It's not minus sign. ds is imaginary.
Yeah. I see.
So in that sense, it can't even obey a triangle inequality because it's an inequality between real numbers. But if it was bothering you that this is a minus sign, you can also make other triangles in different directions. You could consider this triangle. Okay, and whatever you do, you can see that there are situations where triangle inequality is not true, that sum of the lengths of two sides is greater than the length of the third side. The only thing you have to remember is that length is not in space-time, length doesn't have any meaning. Length is a coordinate dependent thing which can be changed by a Lorentz transformation. So we are not talking of length, we are talking of the thing that the metric defines. That is our new concept of length. It's a space-time length. And actually we always work with the square just to avoid imaginary numbers. Yes?
How are we even comparing the lengths since one is imaginary?
We can't, so exactly, so no triangle inequality. The lengths aren't even real. So the first thing, you see, I said that positivity is not there. If positivity was there, then the lengths would be real, then I can compare them. So in a way, no triangle inequality already is guaranteed because positivity is not there. Yeah.
A condition for defining a metric is that you have the triangle.
Yes, it is a condition on a Riemannian metric. First of all, it's positive, and secondly, there is a triangle inequality.
This is not okay.
This is not Riemannian, it's pseudo-Riemannian. We are focusing a lot on the pseudo part. But the really important aspect of the pseudo part is that we are changing coordinates not just of space but also of time. It is not something Riemann could, in my opinion, have ever imagined. He wasn't talking about changing coordinates of time and space together. That every new coordinate of time or space is a function of all the previous coordinates, but only such that this quantity remains invariant after that change. This change you get by the change of coordinates. This one you get by changing it as a tensor, and that change is exactly opposite of this change. Now we'll go into the details. But as I said, first let's talk of his experiment. So unlike Galileo, Einstein simply said, let me be in a lift or elevator, as some people like to call it, and let it be falling freely. Okay? Now, if it's closed on all sides, I'm actually weightless, but I have two interpretations. One interpretation is that there's no massive body called Earth near me, I'm in outer space. The other is that I'm falling to a massive body, but I'm falling freely in its gravitational field, and so I'm not experiencing any acceleration. Both ways, I'm not experiencing any acceleration in a falling lift. Okay? If I leave a piece of chalk inside a freely falling lift, it stays there in the lift. Actually, what's happening is I'm falling, the lift is falling, the chalk is falling, all are falling. But relative to me, the chalk doesn't move because my falling is free. Okay. Now, why was this possible? So, free fall is indistinguishable from absence of gravitational force. So this is the observation, and the way he thought of it, the result is something everybody knows, everybody knew also before. You didn't have to use a lift, you could use various other things. You could just imagine that there are two pieces of chalk, or you have a piece of chalk with something stuck on it, and you drop it. In the frame of the chalk, that thing which is stuck is not moving. That's an example. So this dates back from Galileo's original experiment, showing that different bodies of different mass fall at the same with the same acceleration in the field of gravity. But why is that true? It's true because mx double dot is equal to mgh. This is Galileo, and m cancels. Why does m cancel? Because it's the same quantity. Why is it the same quantity? Okay. There should not be any mg. Mg, sorry. Okay, mg. Yeah, otherwise I could have written it in potential, mv squared and mgh. Okay, good. So why does it cancel? Well, these are actually different physically, as defined physically, they are different quantities. This one is called inertial mass. And it's defined by asking that given a known force acting on an object and experimentally seeing the acceleration, I divide the two and I find its inertial mass. It tells me how the object reacts to a force, right? People are looking very blank, and I hope you know Newton's laws, because you should have learned them in school. Okay, so this is inertial mass, is defined by response of a body to a force. This one, on the other hand, is the response to gravity. Okay, or you can call it the coupling to gravity. If you think carefully, this term is very much like the term in electrostatics, for example, where this would be replaced by Q, the electric charge, because that's what couples to the force of electricity. More charge, more the body reacts to an electric field. Here, more mass, more the body reacts to a gravitational field. And these are logically distinct, and it's an experimental fact that they are equal. It's called gravitational mass. Now, Einstein's thought experiment works only because of this coincidence that gravitational mass is the same as inertial mass. Otherwise, there wouldn't be a frame in which the force of gravity cancels out. There would not, it just wouldn't happen. So it was this equality which made him realize that there must be a frame in which gravity force can be removed. Now, let's try to interpret this in the language of pseudo-Riemannian geometry. Okay, because there is Earth, there is a metric. The Earth has a metric. Every gravitating body has a metric. We'll be calculating those metrics. That metric creates a gravitational. That metric actually is the gravitational field. Okay, and the fact that in the frame of the lift you don't feel it means that there was a coordinate transformation from the ones which are at rest on Earth to the ones which are at rest in the lift. And in that coordinate transformation, the metric has gone back to being Minkowski.
Could you explain that again?
Yeah. So absence of let's write it in a few steps. So let's first agree on this statement. If the metric is Minkowski, then there's no gravitational force because I don't experience, there's no force on me. So we identify, we said that G mu nu is the metric is what defines the presence of gravity. And so the special case, the trivial metric, the analog of having no field is metric is just eta mu nu. A slightly subtle point here, say in electromagnetism, when we say there's no electromagnetic field, we mean A mu, the vector potential, is 0, not 1 or 2 or 3, it's 0. But in the case of gravity, there's a difference, and G mu nu cannot be 0. If G mu nu was 0, there would be no physics at all. Space-time would just not exist. So the correct statement is that G mu nu goes to 1, or whatever 1 means in this context, and 1 actually means eta mu nu, because it's not exactly 1. Yeah. Question? Okay. Okay. So in the lift, no lift frame, no gravitational force. So lift frame metric but in the earth frame there is a gravitational force and G mu nu is not equal to eta with G mu nu of x. Let's give some coordinates. So in the lift frame with coordinates x prime mu and earth frame with coordinates x mu. Okay. So changing my frame of reference from earth to lift means I've gone from x to x prime, and so when x mu goes to x prime mu, this is not any transformation, this is the one exactly which takes me into the lift frame. In this it's an example. G mu nu goes to G prime, which is a by tensor transformation, but this one ends up being eta mu. Now with this logic, we see that the moment there's an acceleration, you'll see all you can say is there's a G prime mu nu. And you can't say whether that is a gravitational force or it's some other reason, because there's no other reason. The only thing you can really measure is G prime mu nu. You measure it in your frame. If it's not eta, then you say there's a gravitational force. And if it's eta, then there's no gravitational force. And the lift example shows you the possibility of eliminating a gravitational force by going to a different frame. Now, the good thing with, now of course we have, the whole rest of the course is to explore the consequences of this. This is a grand idea, it has lots of consequences, including experiments. And now we need to think through how, I've just used a lot of words, now we need to think through what does it all mean, what are we going to calculate, how are we going to compare with experiments. All that is what we have to do next. The second half of the course in particular will largely be comparing and calculating how bodies move in this new theory and seeing whether it agrees with things that we already know. But these are the concepts, and there's already a fatal flaw in this lift experiment. Do people know what it is?
If we make the lift with
Good,
large
thank you. So we said very kind of in a very idealized way that a small point-like lift, if I'm in it, then I can eliminate the force of gravity. But there are two ways I can make a lift where I can never eliminate the force of gravity. One way is to make a very long lift. Okay? Let's say half a kilometer or a kilometer high. Now you know very well that the Earth's force of gravity here and here is not the same. Let's first take the lift to be stationary. It's suspended in the sky, and the gravity measured here and here are absolutely not the same because it's an inverse square law, and this is big enough to make sure that the gravity field has changed. Okay, now I let the lift fall. What will it actually do? It's a rigid lift, then there's going to be really a problem because this one would like to fall according to the gravity force here, that would like to fall according to the gravity force there. So what I could do is I could actually keep some sort of small ball over here and here, loosely anchored at the bottom and top, and wait and see what happens as the lift falls. Okay. But this one is experiencing strong gravity, that's experiencing weaker gravity. So at some point, well, I could keep some space, I guess, because I think they move apart in the end. The distance between them will increase, and that's a measurement in a sealed lift of the fact that I'm in a gravitational field, which I can't remove by just being in the lift has not removed it from me. So let's write that conclusion. Okay, let's draw the second experiment which you suggested. I make the object very wide, and here's the earth. This is my lift. Now this one is attracted to the center of the earth, and this is attracted to the center of the earth. So of course both forces can't be cancelled out by moving the lift. There'll be a residual force where this one wants to go that way and that one wants to go that way, and so they'll actually move closer. So both these examples show that actually gravitational field cannot be cancelled by a freely falling, by going into a freely falling frame. First we said it can, and based on it we made some rules, and now we are saying it cannot. So the original rules were very approximate. Of course, if I make bring these two very close, then this is not going to have any effect. Similarly, if these are very close, then the difference of the field will not have any effect. Here the field is same in magnitude but different in distance. Here the field is same in direction but different in magnitude. In both cases, we can't cancel it. Clear that we can't cancel it, right? Okay. Now we need to recover all these facts from equations. This is a true statement, but we actually have a very nice experimental observation of this fact right here on Earth. Do people know what it is? And a very ancient observation. There's a known physics fact about the Earth, which has been known for centuries, much before physics developed to this stage, which actually captures this fact. Good. So, this is called tidal force. So let's think this through. Earth is actually, what is Earth doing? It's just a ball suspended in empty space, and the only thing that is acting on it is the sun and maybe the moon, much weaker and not doing much, and then a bunch of planets, and whatever is the average field, which is mostly the sun, but there are some small changes due to planets, is freely falling in that. Freely. So in fact, there should be no gravitational field on the Earth from any other source. We should not be pulled towards the sun or the moon or Mercury or something, and that so far that's pretty true. We are not actually pulled out of the Earth. That's because the Earth is freely falling, so we are like the object stuck on the chalk. Chalk freely falling, object stuck on the chalk also freely falling. But the Earth is pretty large, and the gravitational field experienced at different points on the Earth from the sun or from other sources is not exactly the same. Okay, this effect, exactly this effect. And that means that objects on Earth will experience a gravitational pull, in this case from the moon, which will be not the same for every object in different places. Some objects will move to some other place, and that's what happens to the sea. The sea experiences tide. So the general term for this is tidal force. Hopefully by the end of this lecture, so these are all again words. You might ask a question like, how big does this have to be so that I can see this effect? Or how long does that have to be? And we have to figure that out, and it's a question of doing some partial differential equations, calculus, and we will figure it out in a few minutes. Are there any questions up to now? I admit this is all words, but the words are the basis of what we are going to do next. So is there any confusion about these words? Yes?
Yesterday we, I think in like what we did here was model a potential by assuming a different like we saw that if I change the metric of the space that
Hmm.
the parameter is moving
Hmm.
in, we see some disturbance. Are we doing the same thing over here?
Okay, so there's a so there's you're almost right, but there's one thing which I should stress and which I maybe didn't stress enough. In the case of Riemannian geometry, I can certainly take a simple geometry and make the metric look terrible by doing some terrible coordinate transformation. But I can also have a space where there isn't any simple metric. There are only many terrible metrics. Some are more terrible than others, but none of them is Cartesian metric. Such a space is the sphere. It doesn't admit a Cartesian metric. Okay? We haven't yet given the precise definition. What is it that tells us a space is curved or not curved? That's called curvature. And I've tried to steer away from the word because it's again calculationally a bit difficult, and it should come either today or in the next lecture. Okay. Beyond, other than that, what you say is right. I mean, we are talking of changing frames. So I could also, the point is, supposing I am not in any gravitational field, and now I just get into an accelerated frame. Okay, obviously I'll feel an acceleration, and I'll say that it's a gravitational force. But in that situation, all I have to do is come to rest, and all the gravitational force will disappear, including tidal force. All forces will vanish. Then I'll say, actually, I'm in a space-time where the metric really is eta. Just by being in the lift, I was experiencing some weird lift which is zigzagging everywhere. I was experiencing some forces. But when I'm in a situation like near the Earth, when I can make the average force go away by a choice of coordinates, but I can't make the full force go away by that because of tidal effects, then I can't say that I'm in a trivial geometry. I'm actually in the geometry of the Earth. So the geometry of the Earth could be called non-trivial. The geometry of outer space can be called trivial. Eta, the metric is eta, outer space with no massive bodies anywhere. Then the metric is eta. And I can still experience acceleration if I behave weird, but I can also learn that it's just my weird behavior. It's nothing to do with the world outside. By doing more experiments, I learned that it was only my actions that made it look strange. The analog for Riemannian geometry is like you have flat space and then you go to polar, or I gave you some weird coordinates, ad hoc coordinates or arbitrary coordinates, random coordinates. Things look weird, but they really aren't. But the criterion, and in fact, you might ask the following question. If somebody gives me a metric, whether Riemannian or pseudo-Riemannian, how do I tell just looking at it that this is a serious thing or it's just a figment of some choice of coordinates? And answer is not simple. You have to do quite a long calculation, which is what we'll do. Yes?
The experiment you were talking about the lift and actually
Yeah.
the Earth. I mean, you talked about that the lift is like really small, and I think
Initially it was really small, and that means that I can eliminate the effects of gravity by freely falling in that field.
But can you really reduce the effects of gravity?
Have you been in a freely falling anything? Okay, I mean, Stephen Hawking at a stage when he was absolutely confined to a wheelchair and not mobile, insisted that he should be taken up in a plane to experience weightless flight. It's not very expensive to do that. If you people watch Big Bang Theory, there's an episode in which they do exactly that. You just have to pay money and they'll take you up, and then the flight will freely fall for a certain amount of time, not long enough to crash, obviously. And in that half a minute or 1 minute or 3 minutes, you'll be weightless. Now, you can do fine experiments.
There'll be some.
Tidal force, yes. But
Okay.
but you can actually, in principle, you don't have to go yourself. You can send up probes which are smaller and smaller and see that in a very small probe, let the probe have a lot of particles inside which are free to move. You'll see that they're not moving when it's very small. And when it's very big, they're moving exactly like this. So it's completely consistent with this prediction. Now wait for the calculation, then you'll understand what this prediction is coming from. We haven't done that. This is simply the way of thinking. Okay. Good. Yeah.
We're still assuming that the force of gravity is like 1 by r square and everything.
Not necessarily. No. We're just this is okay. It is roughly 1 by r squared. That's enough to create this. But we're not assuming it's exactly 1 by r squared, and in fact, it's not.
Okay.
It is whatever Einstein's equations tell us. But in most systems with most possible level of accuracy, it is 1 by r squared. That's all. That Einstein's theory says that if you do good enough experiments, it won't be that. Actually, nothing is whatever you were taught earlier. I'm sorry to tell you this if it makes you very sad. Coulomb's law is also not 1 by r squared if you include quantum effects. Good. So now, I'm sorry that we got this, well, I suppose it's important to have the discussion, but I had a lot of calculations to do. So let me recall. So now we should ask the question, what is the equation for x mu in presence of a metric G mu nu? This is how a body with whose space-time coordinates are x mu behaves when there's a metric G mu nu of x. There must be some equation to determine it, right? So what is that equation? How do we find it? So the inspiration for finding it comes from yesterday's lecture, where we answered the question not in the context of relativity, but just in the context of extremizing distance. Don't take that calculational part too seriously, because we are not asking about a non-relativistic particle. We are asking for a particle in a pseudo-Riemannian geometry or Lorentzian geometry. But the analogy is, this particle also, since everything in physics seems to obey some principle of least action or minimize something, it should make something stationary. That's the way to derive laws of physics. Okay. Now, in Riemannian geometry, we already saw that making this stationary why is this room full of the smell of some paint or paint thinner? It's getting stronger and stronger. It's like maybe pesticide. I don't know. No, I don't think that's it. But I think it may be safer to open the door. It's not better or worse outside. Let's hope it goes. Okay. This implies the equation, Riemannian, so it should be ij. This implies xi double dot plus gamma ijk of g x dot j x dot k equals 0, geodesic equation. Okay, so for pseudo-Riemannian, we have instead this. And we like to make this stationary. And the problem is, notice that here we have a parameter, this dot, which is d by dt, which is the time.
Yes.
Now we should get a similar equation, but problem is what should play the role of time? The mathematical manipulations are actually the same. The equation we get, we can easily guess that it should be this, where everything is calculated with the pseudo-Riemannian metric. But what is the dot? It's d by d what? Now, supposing it is, so if you say time, then we have to say time in what frame? Why didn't we have to do that yesterday?
There was no time.
Because time was independent of my change of coordinates. My change of coordinates was only being done on space coordinates, not on time. There was a universal time in yesterday's discussion. Now there's no universal time because x mu can change to x prime mu of x mu. So in fact, we define what is called the proper time, and that is actually g mu nu dx mu multiplied by minus 1 over c squared and square rooted. This is equal to d tau. Exactly what we defined in Minkowski spacetime. And again, it's very reasonable. If it was a good thing there and it was invariant under Lorentz transformations, It will be a good thing here because it's also invariant under general coordinate transformations by construction. Okay?
So you
Yeah.
mean we construct G mu in such a way to make it?
No, we don't. We construct G mu nu first.
Okay.
From that we calculate the proper time.
But how do you know that? This thing will be invariant.
This is invariant because G mu nu will transform as a tensor, just like yesterday. The same rules, except with mu's and nu's instead of i's and j's. Under the general coordinate transformation of these, G mu nu will transform as a covariant second rank tensor. Same, there's no change from thing, except that now the coordinates run over space and time. Okay. So my claim is that having defined this, it is possible to derive this equation where dot means d by deta. Now it's a little complicated because, for example, dx nu by d tau, what is it? X dot nu, it is dt c dt by d tau, dx by d tau, dy by d tau, dz by d tau. And d tau is made up in turn of all the dx, dy, dz and dt. So you have to, in calculations, you'll have to use some partial derivatives and chain rules and all to actually evaluate these things. But it can be done, it's not some huge deal. So, this equation, now we'll revisit this equation. See, if I had to tell you the rigorous derivation of this equation now, I would have to spend about 3 lectures more discussing Riemannian, pseudo-Riemannian and Riemannian geometry. We've only spent 2 lectures on that and we already jumped to something really new. So take this as motivated by the fact that same equation arises in Riemannian geometry. The manipulation is similar because I'm making it stationary. Only the parameter which parameterizes the trajectory has changed. Okay, so I have a trajectory in space-time. Here is time, here is space. And what I do is I use tau to keep track of where I am on this. So this is, let's say, tau equals 0. Then this is tau equals something, that is tau equals whatever tau final. It's a parameter along the geodesic. It's a parameterized geodesic. Same was done yesterday, but then we could conveniently use t as the parameter. Yes? So Lagrangian is a problem and we need to do little extra work for that. Okay? So I've skipped that step. It will take a whole lecture to do this through the Lagrangian because we have to introduce some other issues which I don't want to get into now. Actually, tau is not the unique parameter. There are other possible parameters which also make this equation true. And we need to, that's again something more advanced and we'll come to it. But this equation is very striking. Why? This is the way that any body will fall or move in the field of a metric G mu nu. It solves my question, answers my question. Yes?
If the under root, if ds is like may not be real,
Yes.
if it can be complex,
Yes.
then what does extremizing it even mean?
Yeah, so we extremize, that's okay, we can extremize ds squared. But the problem is that, as you know already, these curves can be time-like, space-like or null. The solutions of this will be geodesics and they'll also be time-like, space-like or null. So there's a lot more work, it will come in future lectures. But the important thing is, this encapsulates the answer to a very key question. How does a body, let's say I take a body of some mass m, how does it actually move in a gravitational field? First thing is, this equation doesn't depend on its mass. That's because the same thing happened. The gravitational and inertial mass is cancelled. That was the basis of this theory. So this is a mass independent equation, but it will be followed by any object that's left alone in the field of gravity with no other force, no electricity, no magnetism, no you standing there with a hammer, all those things. But gravity, yes, fine. But gravity is already encapsulated in knowing this metric. We assume now that we know the metric G mu nu of whatever gravitating system like the Earth, and then a falling body, for example, will obey this equation. And now with this, we can actually calculate the behavior of x mu under the condition that it's at the top of the lift or the bottom of the lift, and whatever tidal forces are there, everything must follow from this equation. In fact, this equation in some approximation must reproduce all of Newton's laws. So all planetary motion must be coming from this equation, and not that we have a potential, whatever it is, gm by r. So this must replace that. So I said the mass of the particle doesn't enter this, but the mass of the object that is attracting it, like the earth, that will enter in g. We'll find a metric g mu nu, which we can say this is the metric of the earth. And it will depend on the radial distance from the earth. It will be spherically symmetric, just like the earth is spherically symmetric. And in that metric, if I do all, yesterday if you remember, there was a long calculation to get gamma from g, some one derivative terms and g inverse and half and all that. If you have gone over your notes, you will get gamma, and then this is the equation we have to solve with some initial conditions. Yes?
So when we will be solving for Earth, will we be considering rotation?
What do you mean considering rotation?
Like, will it have an effect?
Oh yeah, so if the Earth's rotation will actually change the metric, yes, yes. The metric of the Earth will depend on its angular momentum also. That's correct.
Why?
Why?
Yeah.
That we have to see when we solve the equations, but you would think so, right? Gravitational field of a rotating body should be different from the gravitational field of a stationary body.
If it is like a perfect sphere though,
Yeah,
still
rotating. In some sense, if you want to think physically, there are some gravitational field lines. As it's rotating, it is somehow dragging those lines. So there will be some difference in the lines due to the rotation. So this metric will incorporate everything about the Earth in principle. Obviously, we can't calculate the metric knowing every mountain and hill on Earth. We assume the Earth to be spherical, have a given mass, and have a given rotation speed, all of which are measured things. And that's all we need to know. We'll calculate g and then we'll solve this equation. That will come much later, because the question we have not addressed is how to find g. We have only addressed a much simpler question. If g is given, how does a particle move in that field? In electromagnetism, I could do the same thing. If somebody gave me an E and B field, we have this formula that F is equal to QV cross B plus QE. That's what this is the analog of. That formula doesn't tell me how to find E and B. Just as if I have a test particle, that's what it will do. Then I integrate that equation and I find what it actually does. Similarly, this is the equation for the test particle moving in a gravitational field. And it's the geodesic equation again, except that it is a space-time geodesic equation. So Einstein's theory can be in a way reduced to saying that every particle moves in the absence of other forces, but in a gravitational field follows space-time geodesics. So simple, yeah.
Like you mentioned the rotating case, so the reason the gravitational field changes because if we take Earth as the rotating frame of reference, the Lagrangian itself changes.
You can think of it that way. Yeah, you can think of it that way. So rotating frame of reference is definitely non-inertial compared to the original one. So one way I could think of doing it is to take the Earth's field and then transform to a rotating frame. But actually it's little more subtle than that. So we are going to do those equations. Those are called Einstein equations. Those will be the analog of Maxwell equations. As I said, QE plus QV cross B doesn't require you to know Maxwell equations, because E and B are given and you find the motion. But to find E and B, you need Maxwell equations. So similarly, those equations will take a while to come. Those will be Einstein equations. We are just assuming it's done, and then this is the equation governing the motion in space-time.